All right, so your assignment number 4 is actually released. That one, there has no subsequent programming test to cover that, but I would suggest still give it a try, your best attempt before the submission deadline. It's gonna complete your learning about trees. It's a different problem for you to solve. Pretty simple one, but it can take some time to actually look into it. Let me know if you got any trouble. The makeup lecture for your programming test number 2, I'll release them shortly after our last class on Thursday. Most likely a little bit about the heap construction. I'll talk about it a little bit later. Okay, and there's a bonus opportunity, for completing the course evaluation. It's completely anonymous. If you're interested, we still have some time for you to complete it. Right? It's online. And office hour will be today, Wednesday, Thursday, the usual time. If you want to speak to me, feel free. And during your exam period, before the exam, I will try to host an office hour as well, maybe in person, most likely. If you want to speak to me during the exam period, you can also do that. Okay, we can keep in touch. Okay, and also lecture note template, office hour, TA, the same as before. Any questions? Okay, let's now recap from last time. All right, so let's see. So last time we basically started with the idea about binary search tree. So there are 2 properties you want to really review very thoroughly. Number 1 is about the search property for binary search tree. That's why it's called a search tree. You can definitely review the definition, but given some internal nodes, you want to make sure every node in the left subtree has its key value strictly less than the key value of the root. And symmetrically, every node in the right subtree, they must have their key value strictly larger than the key value for their parents, right? You're gonna kind of apply this search property recursively on every root of the subtree in your binary search tree, right? So we talk about that way of solving, of checking if it's a binary search tree. Another way to check it would be you want to consider the so-called sorting property. Meaning that if you try to, because binary search tree itself is a binary tree. Of course, you can apply it in order traversal, which will give you some sequence, like a linearized version of the tree. And we discussed last time, the linear sequence that's resulted from the in order traversal is also going to be sorted, right? We'll talk about it. Especially, I want you guys to pay more attention to seeing the correspondence between the sequence that's from the in-order traversal and also the original tree from which we run the in-order traversal, right? You want to see the close correspondence. We did it actually from scratch last time. So you really want to pay more attention to it, okay? And we also try to compare like how you do concatenation for the quicksort algorithm, right? So that's something you can also review to see how they kind of compare to each other, okay? That one I'll leave to you to study. And then we talk about some exercises, just about if you actually got some change in your binary search tree. Is the resulting tree still a binary search tree, right? We kind of discussed. In one case, it is still the case. In the other case, it is not, right? So that's something you want to pay closer attention to, especially when we talk about deletion from the binary search tree, which we wouldn't really talk about during the lecture. That's part of the makeup lecture. I'm going to release the lecture recording to you, right? So that's something you can pay attention to. So to really understand about deletion from the binary search tree, you really want to understand about the predecessor, we said, and also the successor about the nodes, okay? That's something you want to pay attention to. And we talk about this general structure about binary search tree. We identify basically 1, 2, 3, 4, 5, 6, and 7. We got 7 nodes over here. You want to see if you do the in-order traversal, what's it going to be the order for traversing them, right? So that's something you want to watch out for. And what's really the minimum and what's the maximum? And then this one here, the way to identify is the largest one that's smaller than the root over here, right? That's something we spoke about last time, right? And symmetrically, this will be the smallest one that's actually larger than the root, okay? So pay attention to them, okay? It's going to be very useful, especially when we talk, when you see the deletion in the makeup lecture. And we also spoke about how you can implement binary search tree. In some ways, it's a little bit easier than the general tree because you don't really have a singly linked node of the children. All you got will be the left and also the right. Right? You guys can review the detail. Of course, in the exam, I might give you either way. Right? I might give you the starter code for general tree. I might give you the starter code for BST node. Either way, right? So just get yourself familiar, maybe during the exam period, just to study for that. Okay? And you can also compare the nonlinear structure here where we got multiple, not unique. successors like a left and right versus if you see a doubly linked node, it's unique successor. That's why we say one is nonlinear, the other one is linear. And then we talk about how you can do in-order traversal on the BST node, right? It's pretty straightforward. We're going to see something very similar, which is about how you can do search on a binary search tree. However, one thing I want to point to you right away. Doing a search on a binary search is not necessarily the same, runtime-wise, as performing a binary search on a linear array. Not exactly the same, but that's something we got to compare. I'll go visualize to you in just one moment. Okay, just keep that in mind. If you're not exactly sure what I'm talking about, don't worry, we'll get there. And then this is the last piece of code we spoke about, how you can construct a binary search tree like this, right? We got 1, 2, 3 internal nodes, and also we got 1, 2, 3, 4 external nodes, right? You can review the details about how to construct them. And today we're going to dive a little bit deeper into this structure here to see how we can perform search and also insertion, especially for search. We're going to do a little bit more code tracing just to show to you. Okay. All right, any question from last time? All right, let's now dive deeper into binary search tree. So what I want to start with will be how we can do searching. Okay. So if you look at the slides, we are now talking about from slide number 9. Okay. So this is more like a principle, right? We talked about like an application for binary tree before in the general tree lecture. So binary search tree, the way you do the search on that is more like a decision tree. You have to make a decision whether you should go to the left or you go to the right. Pretty much like a binary search on a sorted array. Pretty much, not exactly. We'll see. All right, so before I even present to you the code, let's see gut intuition. It's very easy to see exactly what's going on. There are basically two cases when you want to do search. Either you pass, either you succeed in the search or you fail on the search. Let's say if you want to search for 65, 65 is actually here. So that would be a success. On the other hand, 68, you can double check. 68 doesn't really exist in this tree. So that would be like a failure or unsuccessful search. So these are the only two cases. And we're going to actually run these two examples here, and then I'll summarize about the principle for search for you. And then we'll talk about running time, which is more interesting. Okay? Let's talk about this one first. Let's say we want to search for the key 65 right here. Okay? So what we do is we start with the root right here. You simply compare the key value that you're searching for against the node you're looking at. 65 is actually larger than 44. That means we should go to the right, because every node on the left is guaranteed to have their key value strictly less than. There's no use to go to the left. So what we do is we eliminate this particular part from our search space. All right? And I'm going to make a very important remark right away. So here we basically eliminate this subtree from our search space. However, I want you guys to think about, in this particular example, it looks like we are truncating half of the search space. Is it going to be the case in general? Always half? That's the thing, right? We're going to see that. Okay? So you want to see how large have we truncated. Have we truncated like n divided by 2, like in a binary search, in a sorted array? Or can be, we only have truncated some constant amount of nodes from the search space. Okay, it's a reminder, but you will see more clearly exactly what I meant in a moment, but I want to remind you, okay? This is somewhat like a reflection question you guys can think about when you study for the exam. All right, so that's the first step. So we know that we should really go to the right-hand side, right? And then step number 2, we're going to see 88 over here. And we know that 65 is actually less than 88. So we should go to the left. Essentially, we are truncating this part over here from the search space. And by the way, this part here seems smaller than the left half, right? So this is that we're always truncating half exactly, okay? And then we simply go to the left, and this is what we will find exactly here. All right, so we have found it over here, 65. And then what we do is we simply say we have found it, and we simply return RN, standing for return. Return the internal nodes. So this is the internal node where the key value is equal to 65, right? The data value, we are omitting that as detail, from the tree, right? We're only talking about searching. As you can see, searching here is a very important routine over here for you to really understand. So you want to see exactly where the key is in the tree, all right? So this one here, we're just going to return this object here, the node. All right, we'll see the code in a moment. All right, so this is a successful search. And let me summarize right away. So for case number 1. So when we talk about searching, so there are basically 2 cases. Case number 1, if you got successful search, that means the key is really in the tree. In that case, you simply return the internal node with the matching key value. That is case number 1. Right? Case number 2 is going to be very interesting. Okay, more interesting. Let's say we are searching for 68, but 68 doesn't really exist. So it seems like we're going to go all the way maybe to the very bottom of the tree and realize it doesn't exist. But we're still going to return something. In the successful search case, we return some internal nodes. But what about in the unsuccessful search? We're going to return some external nodes. And what's the use of these external nodes? It can be for later insertion purpose. Just keep that in mind. All right, we'll see exactly what I meant. Okay, let's now try for 68. So 68 is larger than 44, so we can safely truncate this part of the tree. All right, and then we go to here. Okay, so we start with here, and then we go to here. And then we try 68 is actually less than 88. That means we should go here, to the left, right? So that means we also truncate this part of the tree as well. And then we try to look at 68 is also strictly larger than 65. So we can truncate the left half and go to the right. So now for 82, we know 68 is strictly less than 82. So we should really go to the left. And right-hand side over here, truncate it. Okay, and then we go to 76. And where should we go? Left, right? So here you can see 68 is also strictly less than 76. And we're going to the left over here. And the left here is a base case, which is external nodes, has no further children. So that will be the node to return. As far as the algorithm is concerned, when you try to do search on some key that doesn't really exist in the tree, you're going to return some external nodes. But what is so important about these external nodes? Let's explore that. Okay? But first of all, let me write it down. So this is going to be returned. This will be returned by the algorithm. And let's now also write down case number 2. And then I'll explain why this return is actually important. Why are we not just returning some arbitrary external nodes? There's a reason for that. Okay, let's now write this down here. So if the search is actually unsuccessful, and then we're going to return the external nodes. And I'm also going to write down some property over here in just one moment. Okay, but let's see exactly what the property is. Okay, let me give a name to this. So let's say I just call this ext. Okay. What is EST's predecessor in the in-order traversal? Predecessor. Anybody? Which means, imagine that if somehow I put something here, let's say some number that's valid, and then I try to do in-order traversal, what would be the predecessor to this particular value in the in-order traversal? What value would it be? 76? Are you sure? I'm talking about predecessor, not successor. 65. All right, guys, if you somehow lost, that means you have some gap over here, right? So just make sure you review from last time, okay? Imagine that if I want to do in order traversal, right? Let's say, let me just go, let's say I do this subtree here. Just do this one here, okay? Let's now be a little more careful here. So let's say I'm trying to do an in order traversal right here, okay? Over here. And let's write it down. If I do in order traversal there, in order traversal, so I'll start with 54, and then 65, and then 76, right? 54, 65, and then 76, and then 82. Oh, beg your pardon. After 76 should be 80, right? I made a mistake. Okay, sorry about that. Oh, sorry, beg your pardon. Okay, after 76, it should be 80. And then after that, we should really get 82, and then etc. Agree? And then you can see that if there was something over here that's stored in the external nodes, you should really follow in between 65 and 76, right? If you do it in order traversal. That's very important, okay? Between 65 and here. So what this means is, after you have returned this particular external node because of unsuccessful search, if you got a reference to this particular node, I can use this as part of a step for inserting something new into the tree. What should be that new thing I can insert into this particular external nodes in order for the whole tree still be a binary search tree? Any key value that's in between 65 and 76 would be okay. Anything outside this range would not be okay. Okay, I'll write this down. You got to think about it. Okay. What's really important over here is for some subsequent. Oh, you know what? I'll write it down. Maybe on the top. Maybe you cannot see that. Okay, just let me just say. Okay, so I put a star over here for a subsequent insertion. This external nodes can be set with a key value k, such that it should be in between the predecessor and successor. So this will be the predecessor, and this will be the successor between these two. All right? So predecessor and successor. Predecessor, successor. All right? So that's something you want to review from last time. Such that k should be in between 65 and also 76. Okay, let me now do a recap. Oh, before that, let me just make sure. With the key value k and 65 less than k less than 76. Okay, let me recap. Whenever you do a searching on the binary search tree, if the search is successful, you have found the key, just return the internal nodes with that particular matching key. Nothing exciting, just return it. On the other hand, if you actually happen to have an unsuccessful search, it could be just part of the insertion procedure, which you will see in the next page. In this case, you're going to return some external nodes, and what's important about this external node is it will have some predecessor and successor. When you imagine how to see the corresponding in order traversal sequence over there, that's sorted. Once you see the once you see the predecessor and successor, it will tell you the range of key value it may insert into this. Right? That's really important for you to understand. Right? Any question here? Okay, we'll reinforce this idea once we get to the actual insertion, but now I'm just mentioning that, right? But the searching itself, it just returns the external nodes. But I'm just trying to explain to you what is so important about this particular external node. It cannot be arbitrary. It has certain range of expected key value you have to set it to. Otherwise, the resulting tree will not be binary search tree anymore. Okay. All right, so that's about searching. And then we'll get to insertion in a moment, but let's now look at some code. Okay. Let's do some very quick tracing. So this is really the same setup as the last time. So let me do that quickly. So for this one here, it's simply just going to set up the nodes. So we got 1, 2, and 3 internal nodes. We got 1, 2, 3, 4 external nodes, right? So let's just set up the references, right? So these are the references. So let's say we got N20A over here. And also we got N21 over here. And also we got N35. All right, and then we got external nodes. External nodes, number 1. Also external nodes, number 2. External nodes, number 3. And also external nodes, number 4. Right, for simplicity, I'm not really tracing exactly the parent reference as well, right? That's something we did last time. So let's omit that detail for now. It's not important for the tracing here. Okay. Let's now take a look at the following part over here. Right, we're trying to do some search on the binary search tree. By the way, this so far is a binary search tree because if you do the in order traversal, 21, 28, 35, sorted. Right, it's a binary search tree. And I'm going to trace 2 lines with you. The first one is here. And the second one is over here. Right, so these are the 2. The green one is actually a successful search. And the pink one is actually unsuccessful search. We can see exactly what we just said on the previous page, just to reinforce that. Okay? Let's start with the first one. So let's say we do let's say the first one here, okay? Somehow we're arguing that what's going to be returned from the search is going to be N21. That's what we're saying, okay? So we are going to start with the root right here. And then we're searching for 21. Oh, you can see that we're starting with the root, which is N28. And then we are searching for the key 21, okay? And now you can see 21 that we are searching for is strictly less than 28, which is the key of the root, which means we should go to the left. So we're going to the left right here. And if you go to the left, you will check that what's the key value there is 21, which is indeed matching what we're looking for. So we have found it. What do we return? Just return this particular node. All right, so this is why N21 is exactly that's being returned. All right, so this is a very simple tracing. All right, and then let's see the pink one, which is going to be more interesting. What about we try to search for, let's say, we still start with the root, N28, still the same place. So we still start from here. And we're looking for 33 right here. So you can see 33 is strictly larger than 28. That means we should really go to the right. Right here. And then you can see 35 is not equal to 33. So should we go to the left or should we go to the right? Right? That's something you got to think about. So here, 33 that we're looking for is strictly less than 35. Go to the left. Over here. And then we are reaching an external node, which is a base case. That's where we are reaching. And we are returning these external nodes. External node 3. That's why you see external node number 3 here, aliasing. Right, so this kind of confirmed about the principle we said on the previous page. If you got some unsuccessful search where the key is not really matched in the tree, in which case you return some external nodes. And let's now emphasize the point once more. Okay, you want to remind yourself once more. Okay, let me just repeat. If you think about in order traversal, in order traversal, right? So we start with external node number 1, and then followed by 21, followed by external nodes, number 2, and then followed by 28, and followed by external nodes, number 3, followed by 35, followed by external nodes, number 4. All right, so that's an in-order traversal. And we are now returning basically external number 3. That means later on, if we want to use this node for some insertion, what key value can we insert that into? Any value that's in between 28 and 35 will be okay. But let's say if I insert something like a 27, would that be okay? No, because the corresponding in-order traversal would not give me a sorted sequence anymore, would it? Right? Okay, you guys got the idea. Okay, so let me just say this one here. The key value can be anything in between 28 and also 35. All right. This might be the little bit more complicated concept, trickier concept to understand up to now today, right? But it's not too bad. You just got to be very clear about what's the corresponding in order sorted sequence, and also how to see the correspondence between the hierarchical structure and the linearized structure. That's really the point. Okay? All right, so that's about some simple tracing. And then we should now talk about running time for the search. Okay. You might be thinking, well, it looks like based on the example you have presented so far, it seems to be log n. Not necessarily, I can tell you right away. It really depends on the tree structure. Okay, that's something we're going to see. Okay, let's now, first of all, go to the code over here. Let's just look at the code very quickly, right? Oh, sorry. And then just ignore this for now, okay? So we basically got the binary search tree, which is going to return the tree node, okay, over here. And then the routine is called search, is a accessor. And then it will take 2 arguments, 2 parameters. They got the root, the parents, and also the key we're looking for, okay? So this K over here is the key to search. And this is the root to start with. And there are, in total, 1, 2, 3, 4. 4 different cases. But they're essentially just 3. But we'll look at each one of them. So this case over here is about if you have already reached the base case. For example, if somehow I already reached the external nodes, that means my search is unsuccessful, right? So this one here is going to be unsuccessful. So it might be better if I use this one here. Okay, this one tells me that because the node I'm looking at is external, so it will be unsuccessful. Okay, in which case it's just going to return the external nodes. So the P here is just some external node to be returned. Right, that's case number 1, unsuccessful. And the other case would be if the key for the current node indeed is what I'm looking for. All right, let's say over here. So in this case, I'm going to return the internal nodes that has the matching key right here. For example, if I'm looking for, let's say 21, and I'm just returning this node here, right? So that's this case. And the remaining 2 cases are basically like a binary search. You either go to the left or go to the right. So this is where we're going to be more cautious about how many times do we really have to recur until we get to the base case. That's really how you figure out the recursion, right? So for example, when we talk about merge sort, we talk about how many levels do you really need before you split all the way to a singleton list. We're doing something very similar. All right, so let's now take a look at so this case over here, and also this case over here. So let's say recursive case number 1, recursive case number 2. Either we got less than, in which case we go to the left, or we got larger than, in which case we go to the right. Right? Right? Either way. Hopefully the code structure is very clear to you. It's pretty straightforward code to write. All right, so what we should do is we should now think about the big picture here. Let's say this is our tree. Let's say we're currently just at this P over here, which can be the root of certain subtree, just P, somewhere in the middle, okay? Every time, if you want to go down one level, what's really involved? Well, two things are involved. We have to, first of all, compare what's the key, right? Should we go to left or go to right? Comparison. Number two, we should really call get left or get right. But each one of them is just a constant time operation, right? Just about accessing the references. Okay? So you want to think about, we basically, let's say, if this part over here is level I, and we want to go down just one level right here, right? This could be level I, and this can be level I plus 1, right? Just go down one level. You can go to the left or you can go to the right. Let's say we go to the left, for example, right? Just a little bit easier for you to see, right? If you go there, what's involved over here? There are two things that's involved. Number one, we have to compare the key we are searching for versus the P dot key, right? And the key of the P. Either less than or larger than, okay? And number two, we have to also say, accordingly, we should either go to the left, go to the right. Either we say P dot get left, or we go for P dot get right. Either way, but not both. But if you think about these two together, it's just constant time for each level we go to. But now, how many levels do we need to go to, though? How many? Can we say for sure it's going to be log n? I already hinted to you, no. I'm going to visualize even more explicitly in the next page. So now we got to think about what exactly is this running time here. We know that every time we want to go from one level down to, by one level, we need to do two things, comparison and also get left or get right. But how many times do we need to do that? It should correspond to some measure of the tree. What will be the most accurate way for us to say this? We cannot really use n, like a number of nodes, to express this. Anybody? How many levels? Well, all you got to remember is when you go, I'll point to you, one moment. If you recall, back in the binary tree lecture, right, we talked about measures of the binary tree. We got a number of nodes, which I already told you is not good in this case. What's the other one? Go ahead.
Height of the tree.
Height, not hate, height. Yeah, no, you don't hate it. It's height, okay? The height of the tree. All right, so now there are three ways to express this, right? Let's talk about it first. I'll give you the result, and then we'll talk about which one should be which, okay? The most accurate for you to say that would be big O of H. So answer number one would be big O of H. H is the height of the tree. And I want you guys to do some very quick review after today. Revisit. I'll put a star here, okay? Revisit. Only take you 1 minute to revisit that slide or page. Given n nodes. And we actually say that the height h is going to be lower bounded by something here and upper bounded by something over here. I'm going to tell you the result anyway, but it's good to review that rationale about how to derive them, right? That's something you want to take a look, okay? So this is what we set a very tight and also accurate bound. So this big O of H is said to be very tight and also accurate. Yeah, sorry, it's a little bit cramped, but accurate, all right? Tight and accurate. But another way to say is more like a best case. So for searching, the best case, when you actually got some unsuccessful search, so answer number two is going to be big O of log n. This will be what you hope for. Big O of log n is just going to be the same as binary search on a sorted array, just the same. Okay? So we say that this is the best case and lower bound. So best case and lower Okay, bear with my writing, just a little bit harder to write this way. Okay, okay, A3. And what about worst case? Worst case, it turns out, if you try to do a search on a binary search tree, if you're not paying attention to how to construct a tree accordingly or to maintain the tree accordingly, it will be as bad as a linear search. Okay, so this will be worst case and upper bound. All right, so three things. If you want to give a very precise answer, you just big of h. However, h itself, according to what we said earlier, may have a lower bound, also may have an upper bound. So that means the best case will be log n, and the worst case will be linear. Best case and also worst case. And that one just accurate. So these are three things, but they are not contradicting to each other. You just got to know why we actually got three different versions, depending on what we need. Okay. All right, any question? All right, so this diagram here basically just kind of just hint to you again. So for every level, we just do big of 1, which is exactly these two things we're talking about. But how many levels? It will be exactly just h. But h itself can either be log n or n. All right. Questions? And let's now do a very important comparison. Okay. Focus on these two trees. Can you spend just 30 seconds to convince yourself these two trees are both binary search tree? I presume you're kind of running some in-order traversal, right, in your mind, right, to see if that's a sorted sequence. I presume that's what you're doing. That's a good sign if you're doing that. All right, if you do it, this is a binary search tree. This is also a binary search tree. And if you do the in-order traversal for both of them, you're just going to get this particular array. All right, so that's something I want to start with, and then I'll tell you exactly the point, which is important, okay? So if you try, let me call this one here, let's say binary, okay, let me say this, beg your pardon. So let's say this is N1, okay? And let's say this is N2. Two different roots. And then if you try to do in order traversal on N1, it's going to give you, okay, when I say equal here, I don't really mean assignment, just mathematical equal, the same contents, right? It will be the same sequence as in order traversal starting with N2. Doing in order traversal here and doing in order traversal here will just give you the same array, A. Okay, A is right here. Will just be A. You can also verify maybe a little bit later. Okay, the same. They're both binary search tree. However, we say that the left-hand side here, the binary search tree, we say that it's very balanced. I'll explain that in a moment. We've got to define that formally as well towards the end of today's lecture. I'll get there. For now, just understand that intuitively. And this one here, we say that it's unbalanced. And I'm saying these two words based on the heights relative to the number of nodes we have. For example, let's say on the left-hand side, the number of nodes, you can take my word for that, is 15. We've got 15 nodes over there. And also on the right-hand side, it's the same. Also, n will be just 15. However, if you look at the heights of the two trees, very different. On the left-hand side, what's the heights? Can you tell me? That could be an exam question. Simple one. Integer value. What's the heights?
4.
Are you sure? 5? Okay. Height, by definition, is the maximum depth of the descendants, right? Just remember that, okay? Good. So the maximum depth should be right here. 1, 2, 3, 4, 5. Okay. which is about log n.
So like you don't count the like external node?
Over there? You don't really count that. Actually, external is really for like a sentinel nodes. You don't really count that. Yeah. So the question was, when we see the heights, external nodes are really just for like improving the logic of your code. So we don't really count that. Okay. Yeah. So 1, 2, 3, 4, 5. Okay. And then, what about here? The heights is actually about 7. Which is roughly n over 2, linear. We'll see later, sometimes the tree structure can be even more extreme. Maybe it's not exactly n over 2, n over 2. It could be 1 and also n. Right? It depends, right? Just saying it's not very balanced. The most balanced binary search tree you can have will be when you have the lower bound for the heights, basically. That's the point. All right? So we got this and we got this, okay? And what we want to do now is to compare how we do searches on these two and see how one actually corresponds to linear search and the other one corresponds to binary search. That's really the insight I want to give to you. Let's start with the more efficient one, okay? Let's say we want to search for the key 80. Let's start with this one here. Let's say I want to search for 80. And for the sake of efficiency, I assume you guys already know how to do the search. So would you agree? I'm going to follow this particular path. Larger than 44, so I go to the right. Less than 88, I go to the left. And larger than 65, I go here. Less than 82, I go here. Larger than 76, I go here. And then I have found it. Right? So what we're doing is, we basically have found 40, let me just do it again. So we start with 44. And we go to the left, we go to the right. And then we go for 65, about here. And then we go to the right. And then we go to 82, which is over here. And then we go to the left, which is right here. And then we go for 76 right here, and we go to the right, and we have found it right here. So that's exactly how we understood about binary search on a sorted array. Okay so far? Right? So that's why it's log n. Okay? So here, point number 1, searching 80. So let me call this one here BST number 1. And this one is BST number 2. So searching the key 80 on BST number 1 is roughly this, it's approximately the same as performing a binary search on A. And of course, A is sorted. Of course, you can do binary search on that, right? So the main thing is we're now talking about a binary search, performing a binary search. Okay, log n. Running time. Now, let's see what's going to happen on the BST2. And let's say I want to search for the key 97. Let's say that's what we're going to do. Okay. We start with 54. 97 larger than that, I go here. 97 larger than that, I go here. You will go all the way and found this 97. Right? Agree? So the search path will go something like this. We go to the right all the way through, in this particular case, all the way. Okay, all the way until we reach the button there, and we found it. So this is where it is. Now let's see the correspondence in the array. Okay? If you look at that, 54 right here. 65 here, 76 over here, 80 here, 82 here, 88 here, 93 here, 97, we found it. What does that correspond to? Linear search. It's not really binary. We're not truncating any search space. So performing a search on a binary search tree does not necessarily always give you the corresponding binary search on a sorted array. It might correspond to a linear search if the tree structure is unbalanced. That's the main insight we are having here. Okay, let's write it down. So here we're going to say searching 97 on binary search tree number 2 over here is about the same as performing a linear search on the sorted array A. And linear search, linear time. Much worse, but it's possible. Any questions? All right. Okay, if you're okay with this, let's now try to move on. Maybe with another 5 or 10 minutes, and then I will actually take a short break. Okay. So once we're done with this, we just want to talk about insertion very quickly. Okay, about into the binary search tree. This one here just a little slight extension to the searching that we talk about. So in order to insert into the binary search tree, you got to do a search first. Okay, I'm going to just run the example together with you. Okay, so we're done with the searching, and also we did a runtime comparison. So when you go to slide number 14, pay special attention to this table over here, which is what I just discussed with you guys, right? It's a little bit more summary. Okay, look at slide number 14 more carefully when you study. Okay. And about insertion, right? For insertion, let me discuss with you visually. You'll be very quick. If you already kind of understood about how the searching works, just some slight extension. Okay. Let's say I want to insert this entry into the binary search tree. The entry here has the key 28 and Suyang as the value. Okay. But of course, we're going to use this key over here. So this will be the key, and this will be the value. That's the entry we want to insert into a binary search tree. All you do is start with a search. So I'm going to start with the search 28. All right. 28 less than 44, go this way. 28 larger than 17, go this way. 28 less than 32, go this way. So I have found it right here. So what do I do for searching? Return the internal nodes, right? So I'm going to sketch the steps for insertion, but there will be some exercise on the slide for you to try to implement this, right? That's something you can try. So you're going to return the internal nodes with the key 28. So this is already some existing node. All you do is you can say this node, this entry does set value to be Suyang. You don't need to create anything new. Just set the value to be different. Okay? You can say something like, you can say the node return dot set elements over here. You can say Suyang. So these are the two steps. Search first, and then change the data value for that particular internal nodes. That's all you do. Okay. What about second case? For the second case, we follow a similar procedure. You're going to search for 68. This is going to be unsuccessful search, which we knew how to deal with them, right? So let's now try to simulate it. So let's say we go for 68 larger than 44, 68 less than 88, 68 larger than 65, 68 less than 82, 68 less than 76. That means we're going to return this internal nodes. And by the way, we know that that internal node has the predecessor 65 and has the successor 76. That means any key value that's in between 65 and 76, indeed, 68 is fine, right? So this will be the step. Number one, you're going to return the external nodes. This one here, okay? I would say EXTN. And once you have got the external nodes, all you got to do is convert that external node into internal nodes. We did something similar when we did a mathematical induction, if you can recall. So, and then you're going to say convert external nodes into, okay, I'll put a star here. I'm going to draw it here. Okay, all you do is you're going to say, now that external node will be converted, okay, let's say this. This one here is now being converted into some internal nodes with 68. And of course, that one there will also store the value UNA over here, right? You can see the value here, okay? And then that one there is just going to contain 2 external nodes. So that's what you do. You can also work out the Java code. Just create the objects and set the key and value accordingly. That's all you do, right? So insertion, that's it. Not much to say. You just got to remember the critical step for insertion is to find that key. If the key already exists, you only change the internal node as returned. No object being created. However, if the key you're trying to insert into the tree doesn't exist, in that way you have to do some conversion, like what I'm showing here. But the running time is going to be dominated by the search step, right? Which is going to be big of H, which can be either n or log n. It depends. All right, any question about insertion? Okay, if you're okay with it. So I think we're basically done with this lecture here. Let me just say how we can go forward. We're done with the insertion. You can also look at the slides here for more concrete steps. You can take a look. And then insertion, these are the 2 cases I just illustrated to you. And then deletion here is going to be part of your makeup lecture, which I'll release after Thursday. So deletion here, you want to pay extra attention to it because that one there, we're going to exercise your knowledge about predecessor and successor to really justify why after the deletion, the tree remains to be binary search tree. So there will be 4 different cases to consider. So pay more attention to it. Wait. All right, pay more attention to it, and then let me know if you got any trouble. All right, so that's about deletion, which you will follow through the makeup lecture. And there will be some exercises over here for you to implement deletion and also insertion, right? Give it a try, right? It's actually very practical exercises for you to try. And you already got a starter code in the lecture site. If no further question, why don't we take a short break by taking... Yeah, so we are done with the binary search tree lecture, and let's now start the final lecture of the course, okay? The final one, but very exciting one, okay? At the end of the lecture, we're going to talk about heap sort, but maybe not today, maybe on Thursday, okay, in the last class. Now, by the way, I will talk a little bit about your exam, maybe in the beginning of Thursday, so please make sure you come, and then I'll try to give you guys maybe some information, but your exam is pretty far away. So I think we can schedule some review session, some special office hour. You can still have some time to catch up. I think that's your advantage. Okay. All right, so this lecture here, we're going to talk about many things, actually. And some of them will also be made to your makeup lecture, but I will talk about it maybe on Thursday. So we're going to talk about basically worst case running time for binary search, which pretty much like a emphasizing again from what we said before the break, but doesn't hurt to repeat just once more, give you a slightly different angle. And there's something we're going to talk, something called height balance property. In order for your search on the binary search tree to be log n, you have to make sure you satisfy the so-called height balance property. So far we got search property, we got sorting property, and we got another thing called height balance property. Right? So these are 3 things. And later on, we got another 2 properties for the heap. Just got to make sure you don't really get confused. They're just different properties. And you want to understand what's the purpose for each one of them. And we'll talk about another ADT called priority queue. It's a very practical abstract data type. And then I'll get there. And then for today, we wouldn't talk too much about using a heap. Heap is actually the most efficient way to implement a priority queue. But for today, I will focus more on a more naive implementation using a linked list, which would be a nice way to review what you learned earlier. Or hopefully, at least we can get there. And then we'll talk about the heap data structure, right? So that'll be definitely the focus, maybe a little bit today, and definitely the focus for Thursday, the last part of the course. And something called heap sort. So that'll be really synthesizing everything together. In order to do heap sort, you must have a binary tree that has satisfied the search property, satisfied the sorting property, satisfied the high balance property, and also satisfy the structural and relational property as well. So many properties in order for you to get a heap sort. So heap sort is actually quite a sophisticated algorithm to implement. But itself, or I'll show to you maybe on Thursday. The coding itself is actually incredibly simple. Right? And also time complexity a little bit later. Okay, good. Let's now start with about balanced binary search tree. So I just want to show to you, the heights for the binary tree, we know that's linear. So it'll be as if you're performing like a linear search on the sorted array. That's what we did before the break, right? Just recall that. And I want to show to you how is it possible to have a binary search tree with that kind of linear heights. Want to give you some idea. I also got some exercises for you as well. Okay. By the way, so these two are exercises for you for later. They're pretty easy, but I can also give it a try. Exercises. And while you're doing these two exercises, you want to ask yourself, the resulting binary search tree, what is really the heights? Is it n or is it log n? But let's do one together. So what we do is, let's say you're given a sequence of key values from left to right. And we want to say we start with empty binary search tree. Insert a key one by one. So insert 100, followed by inserting 75, and etc. Okay? Let's say we start with 100 first. That was easy. You just got a singleton tree, 100. What's going to happen if I insert a key 75? Should it become the left child or right child? Left child, right? Okay? You learned about insertion before the break, but this one should be straightforward. Just make it to the left, right? Okay, you got 75 over here. And then 68, further left child. 60, further left. And then 50, further left. And then 1. You have a slanted tree all the way to the left. That one there has the heights linear. Oh, I'm so sorry. This one here, what's the heights? 1, 2, 3, 4, 5. Height is equal to 5, and it is the maximum. Upper bound. If you're trying to perform some if you're trying to perform some search on this binary search tree, it's actually going to give you linear search performance, as if on the array. All right? Don't lose the big picture. After inserting all these keys over here, this tree is a tree. And it's a binary search tree. Because if you try to do in order traversal, what do you get? 1, 50, 60, 68, 75, and 100. It's a binary search tree. It's just that it got some very terrible heights over here. That's going to give you like a linear performance on searching. And you guys are going to do this one and this one here and give it a try, right? It's going to give you a very similar result, but I want you to try. Okay? So this is about how the search performance can be very, very bad for binary search tree. So that's why we want to somehow improve it. Okay? To really improve it, we actually have to, let me make some remark over here. Okay? So binary search tree with big O of n heights. Okay, so that one tells us the searching, also insertion, also deletion as well, which also depends on searching, can be maximum, in the worst case, big O of n. Okay, so that's really the conclusion, right here. And we're going to define something called high balance property, which will be, let me show you the textual definition first, and then we'll visualize it. It's pretty straightforward. You're just going to be very proficient in annotating the heights of each node. Okay, so this one here is what we did. And by the way, this is the definition for the heights. I'm going to use that for our example, right? You can review that definition, just consistent with what we said earlier. And then high balance property, right? Let's now read it together, okay? We're going to say for each internal nodes in the tree, we don't worry about external nodes. For each internal nodes n, we want to make sure the heights of their left child and right child do not differ more than 1. Imagine that I'm an internal nodes. I got 2 children. Their heights, if I do the subtraction and take the absolute value, it must be less than or equal to 1. That means one child cannot be higher than the other child by more than 1, or less or larger than or equal to 2. Okay? That's kind of how I interpret this definition. But let's see how visually that would mean. All right. And these 3 trees are just the same, but let's now focus on this one here. Let's say the question is this tree here satisfy the high balance property? That's the question. Oh, that's the first question here. Is the above tree right here a balanced BST? Okay. Now, how do we tell? So we're just going to annotate each node bottom up from the external nodes. So the default, the base cases would be, we got the external nodes, the height would just be, height would just be 0. 0, 0, 0, 0, 0, 0, 0, 0. Start with that first. And then let's review the definition very quickly. The recursive case would be, we want to get the heights for each child and take the maximum heights of the children. This will be the heights of P's children. And then once you get those heights, take the maximum, and then plus 1. Okay, let's now do that. Right here. For example, let's say here, what will be the heights for this one here? The maximum for its children's height would be 0. Plus 1, 1. Okay. What about the heights for this one here? The maximum for children's height, 1. Plus 1, 2. And then for this one here, maximum would be 0 plus 1 would be 1. And then for this one here, maximum heights among the children, 2. Plus 1, 3. So what's good? Okay, let's now do the left branch. Doesn't really matter the order, right? I'm just doing that, some arbitrary order. 0, 0, maximum 0 plus 1 will be 1. 0, 0, maximum 0 plus 1 will be also 1. And then maximum here will be 1 plus 1, 2. Finally, what is the heights right here? Maximum heights of the children, 3 plus 1, 4. Okay? This will be step number 1. Before you can answer whether or not the tree satisfies the high balance property, annotate the height first for each node. And then you're going to do the following. Okay? For example, for this particular internal nodes, okay? This is the internal nodes I'm talking about. And we say that by definition, the heights of its children should not differ more than 1. The heights will be 0 and 0. So this will be how you calculate. 0 minus 0. Take the absolute value. Is it less than or equal to 1? It is. So this internal node is fine. What about this one here? How about this one here? As far as this internal node is concerned. For that one there, you can see the height will be 2 and also 1. So if you do 2 minus 1, is it less than or equal to 1? It is, right? If you check for every internal node, you will see that the high balance property is satisfied. Okay, you can do that by yourself. Okay, for this particular tree here, it's all good. But here comes the challenge. It is not very likely that the tree always stay the same size, will always stay the same structure. It has to be subject to some insertions and removals throughout the lifetime of your application. Whenever you try to do insertion or deletion, there is a risk. You might actually break the high balance property. So as far as this course is concerned, we just want to identify if the high balance property is actually broken. Let's focus on that first. And then I'll link a little bit to the 3101, which you're going to take maybe in the summer or maybe later. Okay. Let's now answer two other questions here. I'll do one of them, and the other one is an exercise for you. Okay. Let's now start with this one here. So for this one, let's now look at this part here. Let's say I take this tree here, which is identical to the one we just talked about. So this one here already satisfies the high balance property. And I try to insert 55. Okay. How do I insert 55? 55 should really go to the right, go to the left, go to the right, go to the right. Right? So this is where 55 should really stay. Okay? That's what we said about insertion. So that means this one here, rather than external, is going to be converted into 55 and then like that. Are we okay with it? Just insertion. Now the question is, after this insertion here, is the resulting binary search tree still satisfy the high balance property? That's the question. It is still a binary search tree, because if you do in order traversal, you still get a sorted sequence. But whether or not it's still balanced, that's an orthogonal issue. It's an independent issue you got to consider separately. Okay? Let's now take a look. We do the same exercise again, but as soon as we detect anything that's unbalanced, we can stop the procedure. Okay? It definitely makes sense to try with the subtree that's kind of impacted. We start with that. Okay? So 0, 0 here, right? And then maximum will be 0 plus 1, which will give you 1. And this external node is also 0. 0, 1, which will give you 2, right? So also good. And this is 0. And then 0, 2, maximum is 2, plus 1 will give you 3. Have you identified any violation of the high balance property already, right? Okay, let's see. As far as this one is concerned, 0 less, so this one here, if you try 0 minus 0 less than equal to 1, that one's good, okay? As far as this one is concerned, if you try, let's say 1 minus 0 less than or equal to 1, good. However, if you look at, let's say this one over here, doesn't seem to be good. Because if you do 0 minus 2 less than or equal to 1, no, strictly larger than 1. So this is where the high balance property is violated. So the resulting tree after that insertion remain to be binary search tree, but it's not balanced anymore, meaning that it cannot guarantee log n search time anymore. The height balance property violated. Log n search time not guaranteed anymore. All right. And as exercise for you, you can just try it out this one here. Let's say we try to insert 63. Okay, let's say from here, insert 63. You can see what happened. Okay, I want to draw some very quick connection to 3101. We don't really talk about, once you detect the unbalance, like a violation of the high balance property, we don't really talk about how you fix it. In practice, as soon as after a single insertion or deletion, if you identify the high balance property is actually violated, you got to fix it right away. Okay, so in 3101, for example, that one there, you will talk about how to fix or to repair the height balance property, right? And a very common practice is to do something called tree rotations. But you guys don't need to worry about this at all. Just give you a little bit of motivation. So in 3101, you're going to learn about once you identify the tree balance is actually compromised, you got to do some repair. Okay, you got to do tree rotation. There, for example, some tree includes something called AVL tree. Another one is called red black tree. But I just named them, but you don't need to worry about them. That's something you will see in the later data structure course, not this one here. Okay. All right, any question? Good. Okay. I got about 6 minutes. I think today, why don't we just finish a little bit about priority queue, and then I'll talk about a heap from scratch, maybe on Thursday. Okay, let's do priority queue quickly. Okay, I'm talking about slide number 5. What is a priority queue? Okay. So priority queue, I will explain this diagram in just one moment. It's going to store a collection of entries. And we know what an entry is. It's a key and also value. However, one thing to note, here the priority queue, the key represents something called priority. And two entries may have the same priority, meaning that key values do not need to be unique. So duplicates are actually allowed. So it's a different context we are talking about. All right, let's talk about priority queue very quickly. Okay, let's see how far we can go. So this is a priority queue, right? Oh, sorry. So this is a priority queue. So 6, 3, 9, 3, 1, 2 here. So these are the priorities. The lower the key value, the higher the priority is. So that means this is the highest priority. Okay. So let's annotate it a little bit here. So to start with, you can see that here, there's one key value over here. So the key value denotes the priority. And we say that 1 here is the highest priority. And the lowest one is right here with 9. That's the highest key value. Okay. And then notice one thing here. You can see we actually got duplicates of the priority, right? You can see 3 here and also 3 here. It is okay. It's allowed. 3 here and 3 here. Entries with the same priority. In which case, doesn't matter which one you choose. Doesn't matter. There's no ambiguity here. Doesn't matter. Does not matter which entry is chosen. Okay, and then what about remove? Okay, let's talk about one more thing, and then we can talk about some implementation. Remove, right here. And as for the remove, you're going to remove the entry with the highest priority. That means the entry that has the most urgent need to be removed and do something about it. Remove the entry with the highest priority. Okay. And what I want you guys to also compare is that's part of your Maker lecture for written test. Compare priority queue, which we just described, with FIFO. Do you remember what FIFO stands for? First in, first out? Okay, good. Okay, first in, first out, queue. All right. Okay, number one, in a priority queue, the entries are somehow, whenever you try to remove something, from the priority queue, entries remove from priority queue according to priority, of course. Lower to higher, all right? What about entries from a FIFO queue? Based on what order? There's a particular term for that. First in, first out, right? Chronological order, okay? So entries removed from FIFO according to chronological order. All right, so these are the two orders you got to watch out for. Okay, priority queue, priorities, FIFO queue, chronological order. All right, just a quick comparison. First in, first out. All right, give me 30 seconds. I think I'll continue from Thursday on this very quickly to finish the priority queue, and then we'll go to the heap. What you want to think about is this page here is actually empty. Don't look at the slides. Based on our understanding about what a priority queue is, let's say we are trying to use a linked list. Either the linked list is sorted based on the key value, or the list is not sorted. I want you to think about the running time for each one of here. Right? Think about under what circumstances should we really use the sorted list, and under what circumstances should we use the unsorted list. And we'll go from there. All right, thank you. I'll see you on Thursday.